What I want to talk to you about today is how we can learn for smart multifunctional solutions for the challenges we have in the 21st century and how plants can help us to solve these problems. Mark said that I'm trained as a biophysicist and I have really the honor and the pleasure that with my chair the directorship of the Botanical Organisms Link, which gives me access to more than 6,000 species of plants which grow happily in my garden. And what I'd like to do today, after starting with this picture which shows the different fields of biomimetics and different successful transfers of biomimetics, not all of them from my institute, into technical applications in the industry. And you normally discern between lightweight construction, materials, surfaces, interfaces, fluid dynamics, swimming, flying, biomechatronics, robotics, communication, sensorics, optimization, architecture, design. This is a rough, let me say, subdivisioning of biomimetics. It's a very interdisciplinary, very active field. New parts come up, other parts merge, but it gives you a kind of overview where biomimetics is placed in. We mainly work in lightweight construction materials, interfaces and surfaces, but as you can imagine, this has also influences on flying, swimming, driving, on mechatronics and robotics, on communication and sensorics. And over the last years, we especially concentrated on biomimetic architecture because we have there a big collaborative research center with colleagues from Stuttgart and Tübingen, which help us really to bring our ideas into built reality. After this very short introduction, I want to start with something which might be surprising for you. What can we learn from motion in plants? And for that, you have first to understand what are the basic differences in motions in plants and animals. What I show you here is this beautiful movie from the BBC of a running cheetah, and it shows iconographically that the time scale of movements in animals, which is normally between tenths of seconds and several seconds up to minutes, makes it possible for our optical system to recognize them. This was what is different between plants and animals. This is the first big difference. I'll show you later why plants are harder to recognize, or movements in plants are harder to recognize. If you look at the running cheetah and we look how the movement in vertebrates is brought about, then we see that it's based on a complex interplay between actuators, muscles, which are linked to tendons, by tendons to the stiff members, the bones, and these bones are interconnected by localized hinges, joints with gliding parts. And this already shows the consequences of this construction. We have stress concentrations in the joints, and there you have heat production, so you have wear due to friction in the joints, and therefore localized joints are always prone to wear and to fatigue and to failure. You all know it with your elbow, with your shoulder. If you normally have an accident in sports, it's very likely that the bone breaks more often you have problems with your joints. And this is totally different in plants. This is a picture of a tropical rainforest in French Guiana where we worked for many years. And I could also say this is a movie of the tropical rainforest because it's static. At least it's static in the way how we see it. It's not static on a long range, and I totally agree with you. But the problem is that the position or stature of plants or movements of plants are either very slow, they take place in a time scale between several minutes, hours, days, or weeks, or they are very fast and happen within milliseconds. And both make it very complicated or impossible for us to recognize them with our optical system. So a tropical rainforest is a highly dynamic thing, can be seen in this time-lapse movie again from BBC, from one of David Attenborough's wonderful movies. This is how saplings react over days in a kind of clearing tropical rainforest. And this is a climbing plant. We worked a lot on lianas, and these climbing plants are incredibly active beings, but they move slow. So we normally don't recognize them with our optical system. The other thing is that on the other hand you have very fast movements in plants. A nice example are bladderworts. Here you have a suction trap, and the trap sucks in small crayfishes, and you have a trapdoor, and as the crayfish gets in contact with the antenna, which is a sensor organ, then the trapdoor opens. The trapdoor is a very complicated system, several microns big. It has a complex cellular unfolding pattern and is elastically deformable. And this is a view from the inside of the trap on the trapdoor, and it folds away like a curtain in a theater and comes back within milliseconds. And here you see movements of this trapdoor. First I show you the normal velocity, and you will see nothing, I think, or nearly nothing, because it's pretty fast. The trapdoor opening takes place with between 0.5 and 0.7 milliseconds. This is a deceleration by a factor of 1,000, and here you see the complex movement of the trapdoor. And that's really interesting for a kind of transfer into technical applications. And I want to show you more how it works. Here we have looked at the temporal angular change. We looked at the trigger hair, which inserts here, and we measured the movement and analyzed the movement with colleagues from Grenoble together. And you see here that the entire buckling and unbuckling process of this trapdoor takes place in between 3 to 4 milliseconds. But the trapdoor opening itself, the opening movement of the trapdoor, is, as I said, half a millisecond to 0.7 millisecond. And perhaps interesting, the acceleration the crayfish feels is 600 G. So it's really fast acceleration that the poor animal suffers off. And this is, for us, impossible without high-tech methodology, high-speed cameras to detect it. The same holds in a much slower motion. This is an infamous Venus flytrap. And the Venus flytrap, the fast closing motion of the trap of the Venus flytrap. This means here you see an animal creeping in. You see it triggers the hairs, it has to trigger them twice within a special sequence, and then this closing takes place within 100 milliseconds. So much slower, but nevertheless nearly impossible to see. What's already obvious here is that you have no localized hinges. Plants always do motions with elastic deformation. And this is the reason why we looked at a huge variety of different plants and try to understand how movements, and especially how the, let me say, bending during the movement is brought about in plants. We looked first on these so-called planar plant organs or tissues, and all the movements are based on elastic deformation without a localized hinge. We looked, which I will show you in a minute, on this kind of strelitzia, the bird of paradise flower. We looked at flower openings in Ipomea or Lilium. We also looked, as I have already shown, at some active traps in carnivorous plants. We also looked at cone scales in different conifer cones, and we looked at the opening of the indusia and sporangia in this nice fern, and I want to show you the complex movement of this indusium in that fern. This is a maidenhair fern, and it's a time-lapse movie. It takes about 1 to 2 hours depending on humidity, and you see this complex movement of these indusia, and it's purely driven by humidity changes, and it can be repeated without any change in the movement pattern several hundred times. It's a very nice way to see how, without a localized joint, complex movements can be brought about in plants. A next group of plants we are interested in, these have more linear or rod-like plant organs, and they have elastically deformable hinge regions. You have never a localized hinge, but you have a hinge region. One we looked at very intensively was the staminal lever arms of salvia, but we also looked at these sporangia in different ferns, and these sporangia in ferns are also pretty fast. And here you see a sporangium opening again of the maidenhair fern, and it's triggered by hygroscopic movement by drying out of this backbone structure. But nevertheless, you have no real hinge, you have a hinge region. Where you can see it even more nicely is within this Drosera, the sundews. There is a few species of sundews which not only stick and catch the animals by sticking, but also have movements. And what you see here is a Turco-driven catapult snap mechanism of the looked first on these so-called planar plant organs or tissues, and all the movements are based on elastic deformation without a localized hinge. We looked, which I will show you in a minute, on this kind of strelitzia, the bird of paradise flower. We looked at flower openings in Ipomea or Lilium. We also looked, as I have already shown, at some active traps in carnivorous plants. We also looked at cone scales in different conifer cones, and we looked at the opening of the indusia and sporangia in this nice fern, and I want to show you the complex movement of this indusium in that fern. This is a maidenhair fern, and it's a time-lapse movie. It takes about 1 to 2 hours depending on humidity, and you see this complex movement of these indusia, and it's purely driven by humidity changes, and it can be repeated without any change in the movement pattern several hundred times. It's a very nice way to see how, without a localized joint, complex movements can be brought about in plants. A next group of plants we are interested in, these have more linear or rod-like plant organs, and they have elastically deformable hinge regions. You have never a localized hinge, but you have a hinge region. One we looked at very intensively was staminal lever arms of salvia, but we also looked at these sporangia in different ferns, and these sporangia in ferns are also pretty fast. And you see a sporangial opening again of the maidenhair fern, and it's triggered by hygroscopic movement by drying out of this backbone structure. But nevertheless, you have no real hinge, you have a hinge region. Where you can see it even more nicely is within this Drosera, the sundews. There is a few species of sundews which not only stick and catch the animals by sticking, but also have movements. And what you see here is a Turgid-driven catapult snap mechanism of the movement of Drosera glanduligera, which again takes place within a fraction of a second, and it really catapults the prey into the center and digests it. Okay, this is nice basic research, which might be interesting for a biomechanics person as I am, or for an evolutionary person, but what can we learn from this for technical applications? And this is the second thing I want to show you. I want to show you how we got inspiration from these plants for biomimetic facade-shading systems, for a kind of bio-inspired architecture. This takes place in the Collaborative Research Centre, Transradio 141. If you're interested, we have a nice internet representation of this Transradio. And the project I will show you are a collaboration between my institute in Freiburg, different institutes at the University of Stuttgart, and the ETV Denkendorf. The motivation is we want to develop planar, curved, and corrugated surfaces with a hingeless kinematics. And the main challenge is we want to find solutions in botany for adaptive hingeless deployable planar structures in building construction and architecture. Firstly, we concentrate on facade shading systems, because facade shading systems are very important today because of the climatic change, because architects like to build with glass. And many of these facade shading systems have hundreds or thousands of small joints, and they often fail. And the idea is to make facade shading systems without localized joints. The first thing we have brought about, it's about 5 years ago, therefore very quickly. This was a Flectofin, a patented facade fading system which is inspired by the bird of paradise flower. The bird of paradise flower builds a so-called perch where the pollinating birds land on. This perch consists of two petals, and these petals form a kind of cylinder which is open on top. And if the bird lands on this petal, on this perch, as you see here, by the weight of the perch, it's bent down. It makes a so-called torsional buckling, which is not very much like engineers or architects, but biology was very clever in functionalizing it. And then this perch bends down and opens with a huge elastic deformation, and then the pollen can be transferred via the feet of the bird to the next plant. The pollination can take place. This was our inspiration for a facade shading system. Our idea was, how can we use this for opening and closing a facade shading system without hinges? And you see here a first demonstrator of the so-called Flectofin. It's what looks here like if it would be turning around by 90 degrees. Does not make any turning movement. It's just compressed and bent by a piston here on the base, which bends the backbone. And by bending the backbone, the flat closes by 90 degrees or opens. You have no localized hinge, you have no moving parts, you have no friction, and that makes it very resilient in the way you do not need any maintenance. We were very happy and lucky that we found architects who built it already a year later. This was a bio-inspired facade which was built at the thematic pavilion at the Expo 2012 in Yeosu in South Korea. And there they used a further developed Flectofin module which covers this surface and is just opened by bending the entire facade shading module. And it works in nearly 4 years. We have got no information from our colleagues in South Korea, and it seems still to work without maintenance. A colleague of mine was there a couple of months ago, and he says it looks still pretty and it still works. And it's not only beautiful in a kind of movement. The architects like the idea that this building is breathing in air, but it has also nice additional things you can equip it with flexible voltaic elements, and you can use also for supplying this current. You can also put some lights on it, so you can really make a kind of ballet in the night in the opening and closing of this facade. We are still going on improving this facade. We make a double Flectofin where one backbone actuates two of the flaps, and at the moment we build the backbone out of layers of fiber reinforced materials with different thermal expansion coefficient, so it may open automatically if the temperature increases, for example, over 35 degrees. All of this is made, the backbone and the shading membrane is made in one go, in one process by glass fiber reinforced polymers, and it not only can be used in architecture, it can be also used as ventilation flaps in helmets or protectors, which are self-actuated by temperature or humidity. We are just producing some first prototypes with companies which produce helmets for sports or for motorbike racing. But it can be also produced controllable or self-adaptive as flaps in aviation, for example, for air brakes, for cooling of brakes and automotives. But I think it could also be used for different applications in robotics. The next example, again from the field of bio-inspired architecture, is the so-called Flectofin. The Flectofin has one shortcoming. It's a long kind of rectangular system. It's always 3 or 4 times longer than wide. So it has some restrictions in the kind of application. And our architect said we would like to have something which is more or less square-shaped. And then we looked again at plants, and we found the so-called snap trap of the Ashwagandha. It's a closely related plant to the Venus flytrap, but in contrary to the Venus flytrap, where you have a snap buckling, where the two halves of the trap buckle and are actuated in a fast movement over elastic deformation. Here you have a totally different way of movement. The snap trap is driven by hydraulic deformation, by a bending of the midrib of the Speck bone, which connects the two halves of the snap trap, and the snap trap halves themselves remain the shape remains always the same, you have no snap buckling. So it's a nice example of a motion amplification driven by a small deformation of the midrib. Here you have a 20 times decelerated movie. The midrib bends a bit, and by the small bending of the midrib you have a large movement of the two halves of this trap. You see here FEM simulation. Equipped with this information, with a lot of data from biology, our colleague starts to make kinematical models for the abstracted folding mechanism, kinetic models of the snaptrap mechanism of the waterwheel plant using finite element methods, which also helps us to understand better our biological role model. And we found out, for example, that for technical transfer, a lens-shaped actuation zone is much better than a rod-shaped one, because this reduces the stresses and strains at the folds where the two flaps move. By that, our engineers and architects says, let's do some simulation how it may look like on a building, and you see this flexible component can be applied to double curved surfaces, and it really looks nicely due to its motion pattern. And this is what the architects like. You can really play around and make not only very functional solutions, but also beautiful solutions which transport at least a part of the, let me say, beauty of the natural movements. We have a first prototype which already works, again built by glass fiber reinforced polymers, and it's just actuated by a small cushion which is inflated by air, and it can be used for differently shaped surfaces in architectural buildings, like, for example, you see here in this kind of building. Okay. Let's go on. What is the basic idea? How do we work in biomimetics in my research group? And this gives you a very short way how the modus operandi is in developing biomimetic structures. Here an example for elastic architecture. First of all, we look for a suitable role model. We make a screening, we look around, we understand how the different plants work. Here, for example, we have looked at the opening of the oriental lily flower as a concept generator for other innovative façade-shading system. It's an edge-actuated system, which was nicely described by Bahadevan and colleagues a couple of years ago. And then we try to model it. This modeling helps us to test the underlying concepts and are a basis for the abstraction and construction of demonstrators, and also for reverse biomimetics, so that we get, again, more information for better understanding our biological role model. Here we see kinetic modeling of the flower opening process, which is caused, as I said, by edge expansion. Then we try to combine kinetic and parametric modeling. So we try to understand the influence of the table geometry, and you get this kind of, let me say, this kind of room of possible structures and possible forms. Some of these forms are formed in a way that you have no chance to open them by edge expansion. Others work, so we understand the places or the forms which work and which don't work, which again helps us to understand biology better. Equipped with this knowledge, we do abstraction and we build demonstrators for double curved surfaces, which are covered with the flexible components, and then we go into the prototyping, which is nice, because prototyping architecture already means building. Architects normally build houses or buildings as one of a kind, and we can really test our ideas in biomimetics on the full load of users in a prototype, which helps us very much to convince people that it's really worth going on with that. Then we also learn from the simulations and from the transfer into other kinds of materials, into other sizes. Normally we make a small thing big, or we make a big thing small. We learn a lot. And we can go back by reverse biomimetics to better understand the particle role models, and then we feed this new knowledge again into the process. So we have a heuristic spiral, which always, in all of the different fields, the knowledge increases. But that's enough about architecture. I want to show you some more examples of our biomimetic research over the last 10 years, and I have selected fiber-reinforced structural materials and damping materials because they also show a wide range of potential application. If you look at bamboo or the giant reed is Carnivorous in France, and it's growing everywhere. And if you play a so-called wood instrument, like an oboe or a clarinet, then the reeds inside are made out of this stem. This already shows that it has interesting mechanical properties. And if you look at such a stem and such a plant with an eye of an engineer, then you have a complex fiber-reinforced compound material where the fiber orientation is optimized according to the main loads, the fiber distribution is optimized, and the matrix structure is optimized. Here you see longitudinal sections through one of these stems, and stained in red are the highly lignified fiber bundles, and in the stems they nearly run parallel with the longitudinal axis of the stem, because in the stem you have mainly bending loads. And you have more fibers to the outside of the stem, because during bending the stress concentration is higher on the outside of the stem than on the inside. The next thing is interesting, the plant can optimize the structure and the mechanical properties on at least 5 different hierarchical levels, ranging from the molecular level, which means lignin structure, lignin content, cellulose content, over the cellular structure, tissue, organ, to the entire plant. One example is very interesting. You never find delamination in these fiber-reinforced materials. In technical fiber-reinforced materials, you often have delamination because you have a very stiff fiber and a much less stiff matrix. And if sudden impacts or swelling loads, then you often have disintegration exactly at the limit between fiber and matrix. This never happens in plants. Why? Because you have a greater transition in stiffness between fibers and the parenchymatous tissue. Here you see fiber bundles, this cross-section of the stem, and you see here the fiber bundles consisting of different fibers. And what you see by the decreasing red staining from the center of the bundle to the matrix, that you have a gradual decrease in the lignification. On the same token, you have an increase in the cell size, and you have a decrease in the small machine. The big machines can braid diameters of up to 4 or 5 meters. They really can braid the basic parts of airplanes. And what you do, computer controlled, you braid the fibers or fiber bundles exactly in the way, in the amount, and in the angle we give from our biological role model. Parallel ones are good for bending stiffness, 30-degree ones are good for damping, crossed 45-degree ones are good against torsion. And if you do it, you have an endless process. Here you see this braiding process, which also I think looks pretty nice. You have the parallel fibers which are braided in, then you have the 30-degree fibers coming, and then you have the 45-degree fibers coming in, and in the same token you also braid in the function canals by braiding around these steel wires. And this is an endless process, and the braided structure runs into a so-called protrusion element, where you can either equip it with a matrix of duroplast or thermoplast. And it runs out in an endless process, and then finally you have these different types. You have very lightweight ones. This one was braided with natural fibers, hemp, in a biological matrix. This was polylactic acid matrix. This one is made for a big airplane company, and here we have pre-strained Kevlar fibers in to make it very, very stiff. These materials can be used for many different applications. Interestingly, they are already in a very cheap material combination pretty good and can compete with aluminium, steel, and also with dry bamboo. To compare this, we have measured the so-called specific bending modulus, which is the bending modulus divided by the mass. This is important for airplaning especially. And if you build them with very cheap material, which is relatively heavy, glass fibers in a massive matrix of epoxy vinyl ester, then you have a specific bending modulus of 24.9, which competes easily with steel or aluminium. It's a bit less than bamboo. But if you would braid it with carbon fibers in a foamed matrix, you can reach values of up to 30, which is very, very good. I have to say that braiding carbon fibers is not that easy. It's a bit complicated, but I think in principle it should work. In addition to that, these structures have a very good energy absorption behavior. The impact strength is over 325 kilojoule per square meter, and the absorbed energy is higher than 50 joule if you braid one of these stems, which is finger thick and has a stem wall thickness of about 2 to 3 millimeters. So this was, so to say, the first attempt, and now we go to the really interesting stuff, to the branched fiber reinforced structures. The motivation again in this collaborative research center, which as I said deals with architecture mainly, is to develop novel biomimetically optimized branching joints for architecture. The main challenge is to optimize not only form and fiber but also fiber rearrangement in this technical branched fibers composites. And the idea is especially for truss structures in architecture and construction engineering. Again, it's a collaboration with my institute, Universities of Stuttgart and ETH Denkendorf. Where can they be used? The use of these high load-bearing constructional parts, which of branched fiber reinforced composites, are wide-ranging from frames for motorbikes or bicycles, supporting structures in automotive or aerospace, for example, stringers, high load-bearing constructions in architecture. But you can also use these multifunctional lightweight structures in robotics for, let me say, a multifunctional kind of food or other ground parts, because they're very lightweight and can be equipped with sensors and actors. What do? We look at different plant role models and may be surprised why we have selected these strange plant role models, but I will explain them in a second. In architecture, there exist already first ideas which copy at least a kind of the branching mode and of the kind of reduction in diameter in these branched structures, but they do not at all get the inspiration how the branching regions should look like. They are really brute force, let me say, engineering architecture, which look not bad. I think this is, for example, this airport in Stuttgart, this is a building in Singapore. They don't look badly, but they only copy, I would say, 5% of the potential plants have. Why have we chosen these strange plants, columnar cacti, dragon trees, and dwarf umbrella trees? Why we didn't look at Carnivorous or broadleaf trees? The reason is simple. All these plants are very lightweight constructions, and all these plants have a very pronounced arrangement of fibers or fiber bundles in the matrix, which makes it much easier for us to get the information we need to transfer them into technical applications. For example, columnar cacti, you have these wedge-shaped structures which run in an interesting matrix, and they run into the stem with specific angles. But what was of main interest for us here, you always find these indentations on top of the side branch, on the lower part of the side branch, and at the beginning we thought, okay, nature is not perfect, perhaps it's just some misbuildings. But when we looked in detail with our colleagues from Dresden, we found them regularly in different species, always exactly on the same place. And this made us think that they may have a kind of mechanical reason. And if you look at that, here we have made, this is original, how the original cactus looks like. This is more or less a kind of engineering simplification. Again here, and this is a simplification. And you see in the simplification, without these indentations, without these structures, you always have stress concentrations on top. It's a tension stress if you bend the side branch down, the compression stress concentration. And as soon as you use the shape optimization you find in the real plants, then you have a smoothing of these stress concentrations. And the reason is relatively simple, because the stress concentrations are more or less they are smoothed and guided to the sides. So the stress concentration is not any longer on top and base, but it goes into the side because of the fiber arrangement and of these shapes and of these indentations. And this seems to help to reduce drastically the stress peaks if you load the side branch under bending. Then we looked at these dragon trees, and these dragon trees, you have very nice arrangements of fiber bundles which run from the side branch into the main branch, and they make a thing which you can call, they embrace, so to say, the main branch. Is called flange mounting, and therefore again the main forces are not in the zone exactly here, but they are transferred into the main stem, which makes them much less prone to failure. To analyze that, we use different methods. Here you see 3D analysis of the fiber arrangement by serial microtome sectioning and 3D stacking, and you see how these fiber bundles run around. This is the main stem, this is a side branch. They really run around the main stem and embrace it, and therefore they transfer the main loads into the main stem. We also did some magnetic resonance imaging. This is my most beloved testing device at the moment, because you can test living plants without destroying them. You can put the plant out of the MRI again, put them under load, and see how they react to the load after half a year or so. And what information do you get from these 3D scanning things? First, you get information about the outer surface, the deformation during bending. Yellow is a blue is the unloaded situation, yellow is a loaded situation. You get a very nice three-dimensional pattern how the side branch deforms during bending. But what's more interesting for us is you can discretize the individual bundles, the fiber bundles, which run from the side branch into the main stem, and you can see how they change in the unloaded and loaded situation, and you can exactly see the deformation of individual bundles in the branching region. Here I have shown it for 2 or for 3 of these bundles, and you see surprisingly you not only have yellow again loaded, blue unloaded. You normally would expect that all go down in the branching region, but this is not true. Some go even up in the branching region, so the reaction of these fibers is much more complicated than you would normally expect, and this helps us to produce improved biomimetic branched fiber reinforced structures. The last example is a dwarf umbrella tree, and here you see this is the wood of the dwarf umbrella tree, and you see it is a finger-like attachment region from the side branch to the main stem. And you see here with the microcomputer tomography analysis how this runs from the top down, how this side branch is attached to the main stem, and you see these finger-like attachment structures, and they are interesting so far because you can never break off a side branch. It only buckles in, but it still has connection even if it's bent in parallel to the main stem, and this is again very interesting for technical applications. Equipped with this knowledge, our colleagues produced new braiding machines which allows, they patented 2 new methods of braiding fiber reinforced branch structures which are bio-inspired. These braiding machines allow exactly to arrange the fibers and to produce the shapes of the branching region as we have it in nature. And we can produce Y-shaped and T-shaped branchings which are way better than anything which is on the market at the moment. Where can they be used? Okay, one of the patents is together with Airbus. So definitely in aviation and airspace, automotives and train vehicles, we have patented with BMW an axle carrier for the new BMWs, which is made out of carbon fiber reinforced structures. Then in architecture and machines, sports equipment, medical technology for artificial limbs, where they would be interested. But again, they can be used, as I said, in robotics, in different kinds of applications. So last but one example is how can we learn from plants for impact damping, puncture resistant materials, and the field of application again is wide ranging from these puncture resistant clothings, these protection vests to puncture resistant and damping helmets. So impact damping in automotives and protection of pedestrians and passengers, or transportation of hazardous goods. And where did we look at? We look at seeds and fruits. You all have perhaps tried to open the macadamia nut over Christmas, and it's one of the toughest materials existing. By the way, macadamia, it's called a nut, but it's a seed. So everything you can be sure, everything you call a nut is botanically not a nut. It's simple as that. I don't know why, but it's the same in English, the same in French, and the same in German. But anyways, the macadamia seed, which is called a macadamia nut, is very tough. Then we looked at the pomelo. It's a big citrus fruit, which weighs up to 2 kilograms. Which the one we buy in nature, they can weigh up to 4 kilograms, and it has a very well damping fruit peel, which is really great. It damps away a lot of energy. So if you are disappointed if you buy this thing and think it's a grapefruit, which has a much thinner peel and you are disappointed because the pulp is smaller, then you be sure it's a very good adapted structure of nature. And we look at fruit coconuts which combine both. Let's start with the pomelo. Why is a pomelo so well damping? What is the biological reasoning for that? As I said, the fruits weigh between 1 and 4 kilograms, and they grow in trees which are 20 meters high. And if they fall on the floor and the wood split open, it would be a disaster for the plant, because then they become very quickly moldy, bacteria infested, and this is a problem because this drastically reduces the germination capability of the seeds, and it also makes it less attractive to animal vectors which eat the fruit and transport the seed to other places. So there seems to be high selective pressure on these fruits not to split open if they fall down from the high trees. To understand it, how it works, we looked first at the structure, and we can discern 7 hierarchical levels from the entire fruit, peel and pulp, macrostructure of peel, microstructure of peel, arrangement of cells and form of cells, cellular structure, cell components, down to ultrastructure and biochemistry. I want today concentrate on the first 5 levels and what we can learn from these first 5 levels. To do that, we have to do nice experiments. We have to let fall pomelos from 15 meters high to the floor, and you see the pomelo bounces back. But if you drop it from 15 meters, it bounces back about 1 meter. So it loses about more than 90% of its kinetic energy. You all know perhaps these full rubber balls you had when you were young, so so-called, in German they were called super balls, and you put them down with the flumes and you have them again. And the pomelo is an anti-flume, it lays on the floor. And this is interesting because how does this fruit manage to get rid of about 90 to 90% of the kinetic energy without splitting open? And the answer is simple again, if you really got the clue to understand it. The answer is plants, these fruits are very clever in transferring local impacts to global answers. So you hear the surface, the impact of the surface of the impacting zone, and the surface which really gets in contact to the surface of the outer surface of the plant, which gets in contact to the soil, is about 10 to 15% of the entire surface of the pomelo. On the other hand, what you see here with different coloring, about 75 to 85% of the peel is deformed. So you transfer local impact to global answer of the peel because the deformation is the thing which damps away the energy. And in all tests we found the energy dissipated in free-fall experiments from 6 to 50 meters high is between 90 and 95%. That's a pretty good thing to do. And what is the secret? The secret is that the peel shows a very pronounced viscoelastic behavior. We did tests here, we did so-called relaxation tests, so we increased the strain stepwise, and then we measured how the force is changing. You see the force after a force peak always shows a relaxation, and this is due to the viscoelastic behavior of this peel. Here we only tested the peel, not the entire fruit. And this can be nicely modeled by a Maxwell model, which consists out of 1 spring and 3 Maxwell elements. And by using that, we get a formula which looks like that. And this can really model this shape of the relaxation curve very nicely. I'll show it to you here on the fourth relaxation curve. Here you see in black, these are the experimental data, and this dashed line are the model data with the Maxwell model. And you see it fits perfectly, and it consists of a linear spring and of 3 of these different kind of Maxwell elements, which are really easy to be linked with different structures of the peel. So you can really explain how the peel mechanically dissipates the energy by using this Maxwell model. But what's much more interesting is what are the structural bases for this energy dissipation. And for that we have to have a closer look to the pomelo peel. And the pomelo peel consists out of a braided foam, with foam cells which are denser on the outsides and gradually become less dense and become dense again to the inside. And this foam is embedded in a 3-dimensional network of lignified fiber bundles, which you see here. And these fiber bundles, you see here one in cross-section, are closely linked to the foam cells. Here you see one foam cell, the other. And what's interesting, the struts of the foam cells themselves are biological cells. So the mechanical structure of foam is built out of biological cells, and this makes the structure very complicated but also very efficient. And how important this network is for transferring the local impact to global answer, you can see here. Here you see an undeformed pomelo peel where we have painted a grid on top, and you see here one of the bundles, and you see this, if it's not deformed, the bundle is nearly invisible, and if you deform it more and more, then you see that the bundle really becomes more and more visible because it transfers the impact to the entire peel. The next thing we are looking at is how we can make a structure, bind structures puncture resistant, and here the macadamia seed coat comes in. The macadamia seed coat is a highly integrated protection wall, hull, and it's micro-layered. It's very hard and tough because of the micro-lamination of different layers consisting of sclerenchyma fibers and scleroid cells. Here you have a scleroid cell layers, and you have a sclerenchyma fiber layer, scleroid layer, and so on. And by this, all fractures don't go through the macadamia seed gel, but they stop in the seed gel because it has very good and very pronounced fracture stopping facilities. And if you compare a macadamia seed with other nuts, which are the only real nut here, by the way, is a hazelnut. These are drupes, and this is also drupe, and the peanut is a seed pod. Anyways, the macadamia seed outcompetes, if you compare the fracture force to the gel thickness, all the other plants by a factor of 3. So it's a really very hard and tough material, which is perfect as an inspiration for a puncture resistant surface and structure. Then we also looked at the coconut, and the coconut is very complicated because it combines both energy dissipation and puncture resistant. Energy dissipation is brought about by this mesocarp. This is a fibrous structure around, and the puncture resistant is the so-called endocarp. This is a type of coconut you normally buy. This roundish brown thing is just the endocarp of the coconut. And if you look at the structure of the endocarp, again we see these stone cells, and these stone cells themselves are multi-layered structures which are very complexly built. And interestingly, the stone cells are interconnected by something which looks like dovels. And these are lignified plasmodesmata, which you see here, here, and here, and which nicely interconnects the stone cells, but also increase dramatically the friction. So even if they are broken, they are kept together by the friction of these dovell-like structures. And again, it's embedded in a three-dimensional network of these highly lignified fibers. And if you look at that again in micro-CT, you see that these fibers run in from the mesocarp, and then they bend and run nearly parallel with the surface of the endocarp. And this makes them perfect crack stoppers. Because if a crack comes in, and then it meets one of these bundles, then it's immediately deflected and runs parallel with the bundle, which means in parallel with the surface of the endocarp, and will never penetrate the entire endocarp. You see it nicely here in this picture. You see here a crack coming in. This is a cross-section, through here. You see the crack coming in, and as soon as it meets one of these bundles, it runs with the bundles and is deflected in parallel with the surface and never splits the endocarp open. So you have a pretty good lightweight crack stopper thing in the coconut. And if you compare the coconut with the other nuts, then you see it's not as good as the macadamia, but nevertheless it's twice as good as all the other nuts we have tested. Equipped with this, our colleagues made fiber-reinforced graded metal foams and fiber-reinforced graded metal polymer foams. So the metal foams are mainly made for crash boxes in cars because they are very good in absorbing impact energy and protecting not only the driver but also the pedestrian if you run on a pedestrian. And here we have a project which is actually running. This is for protection helmets and protectors for shoulders and knees. We collaborate with the German Olympic skiing team, and we want to protect the skiers against the impact they have with slalom and other things. I want to show you only the results for the metals because the other polymer stuff is still under patenting, so I'm not allowed to show something. Here you have a graded aluminium magnesium alloy with graded size of foam cells, and embedded in this graded metal foam you have mineral fibers, which are very tricky, and the colleagues from the RWTH Aachen had to develop a new method to build it. But at the end they were successful. We had a graded foam with fibers embedded, and we have a layered surface inspired by the macadamia seed gel. And altogether can be really used for different applications in cars as crash boxes, or in this for the transportation of hazardous goods, or if it's made out of polymers, then it can be used for sports equipment, helmets. The last example is self-repairing biomimetic materials. And self-repairing is one of these issues everybody is interested in, but you nearly don't find any technical material which is really self-repairing. On the other hand, biology would not exist without self-repair. Imagine yourself, you cut yourself and blood runs out. If you would have not a self-repairing system, you would just die, because the blood would run out of your body, and that's it. And if the cut would be small enough, you would have time to say goodbye to your boyfriend, to your family. If the cut would be too big, it would be that would be. So you have self-repair at all levels, from the molecules over the cells, over the tissue, over the entire organ. But you don't find a lot of cells, or nearly no self-repairing transitions into technical applications. And that's why we looked at plants, and we found something which was really interesting. In all plants, and then we looked also in animals, you can subdivide self-repairing into a fast phase of self-sealing, which only seals the fissure. The fissure is still present. It's repaired functionally. This is when your blood clots. Blood doesn't run out anymore, but it's not repaired in terms of mechanics, and it's very fast. And later, the so-called self-healing phase starts, which the cut is not any longer present. It's repaired structurally, and at least part of the mechanical properties are restored, and it takes much longer, and much more biology is involved. New cells are built, new materials are built. We looked at 3 different systems in plants which we analyzed that has transferred in different levels. One is the self-repairing delosperma leaves, where if you cut a delosperma leaf, it really bends, and by bending it closes the fissure, and we want to produce self-repairing multi-layer films out of it. It's in the moment we have some first simulations and the first idea of lab demonstrators. Then we looked at the cellular level, self-repairing Aristolochia, it's a climbing plant, and there we developed self-repairing foam coatings for pneumatic systems which are already on the market. This I will show you in a moment a bit more in detail. And we looked at latex plants, Ficus, Euphorbia, and we looked at the molecular level, and here we developed self-repairing elastomers which exist on a, let me say, it's more or less a lab demonstrator, perhaps a bit more. Let's have a look on these self-repairing coatings for pneumatic systems. There a company came to us. This was a company Prospective Concepts. It builds these very nice so-called tenserity structures. These bridges consist of a compression strut on top and tension cables around the cylinder which was inflated by air. They are very lightweight. They can build up within 1.5 hours for a span of 8 meters and a load of 3.5 tons. And they are already built also for roof structures, for example, at Montreux in a parking house close to the railway station. But the problem always is with pneumatic structures. If a hole comes in, air leaks out. That's not a big problem here because the overpressure is very low, between 50 and 150 millibars. So in your car you typically have 3.5 to 3 bars in, so 3,500 to 3,000 millibars, so it's very low overpressure, and you anyways need to deal with changes in air pressure, you need compressors. But nevertheless it would be nice to have a self-repairing coating which closes these holes. And what we did again a screening, and we were very lucky to be very quickly finding a nice example which could help us. These are the stems of the Dutchman's pipe. It's a climbing vine, and vines are not always flexible. In young stages they are very stiff because they have to bridge gaps between supporting structures, and this stiffness is brought about by a closed ring which you see here in blue of lignified fibers. And as soon as the plant is attached to a support, the inner wood starts to grow, and the wood is very flexible here with huge vessels which transport a lot amount of water. But by this growth of the internal wood system, this outer ring is set under compressive and especially under tangential strains. And it splits open as you see here. It splits open here, here. And if these fissures would run to the outside, it would be disaster of the plant because they're ideal in transport gates for bacteria and for fungi. And therefore there's a high selective pressure on closing these fissures. And how does the plant do it? Very easily again. You have the outer cortex, and the outer cortex consists out of parenchyma cells, which you can see as water-filled balloons, which are under an overpressure between 2 and 3 or 4 bars. And as soon as a fissure occurs, as you see it here, these cells swell into the fissure and seal it. So it's not biology, it's physical chemistry. They relax in a kind of opening because you have a disturbance of the stress-strain field in the surface, in the interface between this stiffening ring and the surrounding tissue. If the plant grows further, the fissures become larger, Then you have biology involved, you have cell division in tangential and radial direction, and sometimes you even have a kind of liquefaction which restores a bit of the mechanical structure again. We were interested in this very fast self-sealing phase, and what was our idea? Our idea was that we coat, here you have a membrane of pneumatic systems, this is the inside of the pneumatic system. We coat such a membrane with a closed cell polyurethane foam, which we cure under overpressure. And our idea was, during the overpressure, we have stored the overpressure in the closed cells of this polyurethane foam, and in addition, we have a kind of strain in this foam layer. And the idea is, if you puncture this self-repairing structure, then the foam will swell into this fissure and close the fissure. And this worked pretty well. Here you see one of these membranes, here you see one of the foam coatings, here in SEM of the closed foam cells, and with soft closed cell polyurethane foam coating, the air leakage through holes of up to 5 mm diameter could be entirely stopped in about 90–95% of all cases. In the other 5%, it could be reduced at least 1,000-fold to through holes which are not covered with this self-repairing foam. You see here a nail was driven through, and here you see the nail channel, and here you see how the nail channel is closed. I'll show you quickly a movie twice. This is an uncoated membrane, this is a coated self-repairing membrane. We puncture it, and we blow the foam of liquid air over it, and you see the puncturing, what the puncturing makes in the uncoated membrane. You see it here. It's punctured, the hole is made, and the air leaks out. It blows away the kind of liquid air which always is blown over. And if you look now at the coated self-repairing membrane, then you see, and you have to look very concentrated because it's very fast. Oh, and now it's closed. Now it's not only sealed entirely, it's also sealed very quickly. And this is very important because you have not minutes or hours time to close such a hole within such a hole. It has not to be nearly entirely, but it has to be also very quickly, and we were very lucky to succeed with that. Then we had a problem. We want to measure how good our repair situation is, and there was no definition for self-repair efficiency. Then we defined with our colleagues from the EMPA in Zurich and the ETH in Zurich and from the EMPA in Dübendorf a so-called self-repair efficiency, or flow. And we said, okay, our flow is 1 minus m dot code. M dot code is the air mass flow through a punctured coated self-repairing membrane, divided by m dot ref is the mass flow through a punctured uncoated membrane. And if there is no difference between the coated and the uncoated membrane, so you have no self-repair effect, then m dot code equals m dot ref. You have 1 minus 1, so 0 means no repair, and if an entire sealing m dot code, then the air mass flow is 0, then if 1 means 0, then you have 1, which means complete sealing. And the best results we get with a foam coating of 0.16 gram per square centimeter, so still a very lightweight structure, and with curing overpressures between 1 and 1.5 bar, and you have self-repair efficiencies between 0.999 and 0.998. So more than 90% are entirely sealed, and the remaining the airflow is reduced by a factor of 1,000 or more. And this we were very lucky to get this on the market with an industrial partner, Ramf Giesarts, and you can buy this repair foam under the name Raku Pur 33, blah blah blah. So it's on the market, you can buy it, and it's used in specific applications, but not yet on a wide range, because if you want to use it for cheap rubber boats or cheap pneumatic mattresses, we have to do it in one go when we produce the membrane we have already to coat it with a self-repairing coating, and this is still a bit of a problem. Field of application, wide-ranging: architecture, pneumatic buildings, bridges, roofs, membranous structures for hulls and containers, pneumatic seats, all pneumatic aircraft and watercraft, but also pneumatic robots or fluidic muscles could be equipped with this self-repairing foam coating. At the end, a last slide, and this is very important for me because, as Mark said, I'm involved in biomimetics for quite a time. And I think at the moment biomimetics is really kind of golden period. And the reason is multifaceted. Why? I had a long discussion with Werner Nachtigall, one of the German godfathers of biomimetics, the other day, 2 or 3 years ago, and he told me in the year 1980, when he was on his peak of developing new materials, he said we had brilliant ideas, we had wonderful systems, but nobody was able to produce them. Either it was just impossible, or it was so expensive that nobody could pay for it. Today, Still everything is imaginable, but nearly everything is technically realizable. And why? There are, in my opinion, mainly three reasons why we have a historical chance. This is the recent advancement in analysis and simulation technology. You can nearly understand biological role models and the biomimetic products from the molecule to the entire system. If I say it's cheap, I know cheap is relative. But when I got the last time an offer to change my position in Freiburg, I was asked what they have to give me to stay in Freiburg. And I told them I want to have an atomic force microscope coupled with a laser microscope. And this is about 8 years ago, and at that time this equipment costed about 500,000 to 600,000 euros. We just bought one last year, and now it costs 80,000 euros. So 80,000 euros is still a lot of money, but compared to it, it's nearly 80% reduction. So we are able now to use high-end equipment also in normal labs at universities. Simulation is very important because it helps us not only to understand what we have to transfer, it also helps us to understand the biological role models in the way of reverse biomimetics. So we can really improve our knowledge on the role models and what we want to transfer into technical applications. What's perhaps even more important, for the first time, we were able to produce bio-inspired products to a reasonable price. For the first time, we can make productions from small to big, as biology does. Laser sintering, 3D printing, different methods of all these 3D methods. Then, as I said here, the 3D braiding protrusion, as I showed you. Then here, electrospinning, and a lot of other technologies allows us to produce for the first time similar biology, but also to a reasonable price. And last, and this is a kind of soft thing, but I think it's still important, the social and political environment has changed. So biomimetics has a huge potential for sustainable materials. I have to say that not all biological materials are sustainable by themselves. You have to test it for each solution separately, but the potential is huge. And this is now accepted politically and socially, and the companies I collaborate for many years, I can't show you any examples because it's Modus, it's really confidential with big car companies, and they would have never changed anything without political pressure. Only political pressure and pressure by the community, like VW, what we see now in the States, now in Europe too. They would never have changed the systems, they would have cheated us without political pressure. And this gives us a good chance to bring in new results, new methods, new ideas on the market and also on a mass market. And this, I think, is very important because biomimetics still lacks a lot of mass market products. With this, I want to thank you for your attention, and especially I want to thank my group because everything I've presented they have done, and I want to thank a lot of funding agencies which gave us really a lot of money over the last 10 years. Thank you very much.
Any questions? Yes, Mark.
One of the things I find interesting is you see a lot of very impressive examples of very high specific strength and very good fracture toughness, but not very much in the way of materials that are very hard, except phase tension. And I wonder if you have any speculation about that.
I think hard is not an issue. Nature is really interested in that we make it separate. For nature, it's much, there are some hard materials also in the teeth, for example, which have not only dentin but also minerals in stuff like that. But normally for nature, it's really reduced amount of materials which are at nature's. Look, these are a few fibers and a few matrices, that's all. And for nature, it's much easier to make tough materials instead of making hard materials. And the other thing is with hard materials and hard structures, you often have the problems if they break, then they are really broken. They have no fail-safe behavior. And a lot of nature materials show a fail-safe behavior. Even if they have damage, they still work for 40, 50, 60%. And therefore, I think being only hard is not a solution which is much favored by evolution. But I can't say more. You are totally right. You also are surprised. There are really few very hard materials in nature.
So we have one question with Paul and then.
Yeah. So it's wonderful work, but now the next step, there's a bit what I think about in biological systems don't produce a homogeneous structure. It's often also hybrid, because communication systems are running through the structure. So how are you going to get these more, let's say, hybrid structures where we can combine structure with also these functional properties?
This is what we're actually aiming for in this biomimetic architecture now. I have to admit that I avoided that over the last years, because I started, you will not believe it, I started as a neurobiologist. My first paper was on learning Drosophila. And from that I know how complicated this stuff is. And therefore I thought, okay, if you want to be successful on the material side, avoid all communication between materials. But now we are on a level where we first think that we can have communication between materials. We are aiming, for example, for materials which don't need energy for actuation and sensing, but producing energies themselves. This is one big issue in one of my research projects. And it was a bit of call me a coward. But I said, okay, this is too much for me, let's start with that. But you are totally right. This is definitely the most important thing to do in the next couple of years. And I think for the first time I have the feeling that we can really do it in a way that it has a chance to come on the market. Because I have to say, when I changed from basic research into biomimetics, one of my main aims was only to develop things which have a chance on the market. Because I have seen so many materials die on the lab benches, which are wonderful, but nobody would ever give them a chance on the market. And this was the reason for me, but you're totally right. I hope that in the next years we can develop some of these higher, more integrated things.
Questions there?
Very nice talk. I was wondering, I saw this movement of the plants and how we were inspired by that. So my question, because you mentioned it just right now, has to do with energy. How is activation possible? Because the memory itself is very beautiful. However, I'm assuming that one of the main goals will also be to have more energy efficient approach where we might minimize.
I can tell you for the Flectofin, this façade-shading system, if you could use it out of layers of fiber-reinforced materials with different thermal expansion coefficient, you can make them self-actuating. Then they use the energy from the sun to bend and to open. The problem is, and this is what I'm totally surprised, we were very proud when we had the first demonstration, that that's the solution for architecture. And then our colleagues from architecture told us, and where is the master switch? What kind of master switch? And they say you can't sell a façade-shading system which is autonomous if the inhabitant wants to have it open or closed, independent if it's useful or not. So you always have all these things to add a master switch, and then you lose at least a bit of the energy efficiency. But you're totally right. I think the other ones of Flectofin is very energy efficient because you can actuate it just with compressed air, localized or non-localized. On the other hand, I just told before that we are at the moment working on these energy autarkous materials with colleagues together, and this is the thing which really interests me most at the moment. For example, if you look at a tree, there are a lot of vibrations with the tree bends away, and it normally is then the way we think indeed at the end. But I'm not sure if it's really the case. My idea is that you don't dampen away energy by vibrations which are acting on many technological buildings, but you use this vibration to store the energy internal in the materials, and you can use it later for sensors or actors, which are nowadays so small and so energy efficient that you don't need a lot of energy. So we are working on that, but you are totally right, it's a very important thing to do in the future.
Last question?
On that same topic, the movable member structural members, what about the possibility of controllable stiffness in a structural member?
The Werking structural members controlling stiffness is in by changing the internal pressure of cellular systems. The plants do it with changing internal pressure normally, and they can vary the stiffness tremendously just by changing the turbo pressure inside. We did a bit of changing this. Turbo is a problem because then you have water inside, it's heavy. Air is a problem, it's very light, but it's compressible. So what we did, we tried to change the arrangement of the fibers inside by straining the outer hull. And this works because you can make an outer hull out of fiber-reinforced material which stretches a bit and is self-stiffening. But the problem then is you have to know exactly in which size, in which direction you want to stiffen it. It's a bit of a catch-22 problem. if you know exactly, okay, if I want stiffening in that direction, then it's relatively easy to handle. But if you don't know if the stiffening in that direction or that direction, then it's very hard to implement. But it's definitely a thing we are working on: self-stiffening, self-adaptive stiffening, but also self-adaptive toughening of materials. This is in concrete what we are doing at the moment. We want to produce lightweight concrete in which spheres are embedded into like stone cells and also fibers, so that you can make localized stiffening and toughening exactly where you need it. It's complicated. The question always is, it works also if you make a single building. As soon as you would go on a mass market, you know our building persons. If you tell them, this is a complicated concrete, you have to mix it here like this and forget about it. And this is a big problem. This really is, it's not because they are stupid, not at all. They are under such a high time pressure to produce these things that you have to produce it in a way that it's failure-proof. And this is a big challenge to do to come on the mass market. But this is definitely a thing we want to deal with over the next years.
Okay, thank you very much. Let us thank again the speakers.